Okay, so the next one is exercise 11, and in this one we have to prove that Sn, of course we have Sn, the symmetric group of degree n. Now in this we have to prove that the smallest subgroup that contains these two permutations, this 2 cycle and this n cycle, is Sn itself. In other words, these two permutations generate the entire group Sn. Now before we write the solution, of course, let's just quickly recall what this smallest subgroup, what this thing is. So we know that if we have a group, some group, any group G, in which say you have a subset S, not necessarily subgroup, just some subset S, and we are also not putting the restriction that S is non-empty. S may be empty also. What you can then do is that you can consider the collection of all subgroups of G which contain S. Okay, and let this collection be given a name also. Say we are calling it T. Now the first thing we can note about this collection is that it's a non-empty collection. We understand what the collection is. In it, we have precisely those subgroups of G which have, all of them have S inside of them as a subset. The collection T is non-empty because G itself is one such subgroup. G is a subgroup of G that contains S, because that's how we have taken things. So G belongs to T. That means we are dealing with a non-empty collection of subgroups of G. What one can then do is one can consider the intersection of all elements in T, because the elements in T are after all subgroups of G, so we can consider their intersection. It makes sense. What more is true is that this intersection itself is also a subgroup, and this subgroup is defined to be the subgroup of G generated by S, and it is usually denoted in this text by this symbol. And it turns out, because of how it has been constructed, it turns out that this W is in fact the smallest subgroup of G containing S, and that's what we have here. So we have to prove that the smallest subgroup of Sn containing these two things, that means the S that we have here in this specific case is just this. It consists of these two cycles. One of them is this 2 cycle and the other is the n cycle. For this S, we have to prove that this, say let me call it S prime. To distinguish it from the general S, we have to prove that the subgroup generated by S prime is Sn itself. Okay, so that's what we have to prove. So let's see how we can get a solution. Now in the solution, in the beginning itself, we tackle the smallest possible value of n. Of course you can take n equal to 1, but that however is not allowed here. That's because although nothing has been mentioned explicitly about what n is, but you see 1, 2 has been mentioned. So this must at least be there in Sn. So n should be at least 2. So that's the smallest possible value of n. And in that case, the result is trivially true. We are just going to mention that in the beginning of the solution, and then of course we will see why that is the case. When n is equal to 2, the claim is trivially true. So once we understand how that is true, we can then assume that n is at least 3, because the two cases we will have dealt with it. The claim is trivially true. But how? See, when n is 2, then we have S2, and we know from the already developed theory of Sn that the order of Sn is n factorial. This we have already seen, and we have proved this also. So S2 will have exactly 2 factorial elements, that means 2 elements. One of those elements is of course our identity permutation, which does not change anything, and the other is this 2 cycle, and that's just it, that is S2. It's an abelian group having 2 elements, and in this case you notice that the permutations that are being mentioned in the exercise, they actually coincide, because n is 2, this n cycle and this 2 cycle become the same thing, and the subgroup generated by this sole element, or rather more technically speaking, the subgroup generated by the singleton set having only that element is of course S2. That's because what are the subgroups of S2? S2 has only 2 subgroups. One is the trivial subgroup consisting of only the identity element, which however does not have this 2 cycle. So that's not the subgroup we are seeking. The other subgroup, the only other subgroup is S2 itself. So that's why the subgroup generated by only this is S2. So in this case, things are trivially true. So, or okay, instead of writing now, we write like this. So assume n to be at least 3. Now we will have to go through some calculations, some arguments involving these 2 things, and of course the subgroup generated by them. So we are going to name these things something, so that it becomes easier for us to write the things. And I mean, we do not want to keep writing these things again and again. So let's just call this sigma, and let's call this tau. Let sigma be defined to be this n cycle, tau be defined to be this 2 cycle, and let H be defined to be the subgroup of Sn generated by this subset, that is generated by sigma and tau. Okay. Now let us see what we can do with these things, sigma, tau. the first thing we note is this. Note that for any integer k satisfying these inequalities, we are not of course mentioning for any integer k, but in this context you understand that k is an integer. For any k satisfying these inequalities, this equation is true. This 2 cycle k comma k plus 1 actually turns out to be equal to sigma inverse times this 2 cycle k minus 1 comma k times sigma. Now it's just a matter of verifying that this is in fact true. So what I want you to do is to see, when not just you, when we encounter this type of things which are written generally for some things which are there are many things, right? In fact, we are saying something about infinitely many things. That's because n can change its value, and even for a single value of n you will get quite a few cases for k. So what do you do to understand such a thing? What you do is that you start taking specific values of n. So you take the smallest value of n, that is 3. So in that case k has only one option for it. So in that case k has to be equal to 2 itself. So you will have here 2 comma 3, and you actually see whether this is true or not. You do that, then you take the next value, you take n equal to 4. There you have 2 possibilities for k. For each one of those possibilities you verify this equation. When you do like this, you continue with a few more values of n and hence the corresponding other values of k. You will get a feel for why this is true, and then you think of the general n, and then you will realize that yes, this equation is in general true. But it's something that is true, so we are now going to use this somehow. Okay, so what we are seeing here is that if we set up an element that looks like this, where in the middle one looks like this, k minus 1 comma k. So if we pre-multiply this 2 cycles by sigma inverse and post-multiply it by sigma, then this product turns out to be equal to this 2 cycle k comma k plus 1. And that too, there is one more thing to notice here. Note the values, the possible values of k. The smallest possible value of k is 2, and the largest one is n minus 1. What happens when you put n minus 1 here? You get the 2 cycle n minus 1 comma n. Keep in mind that we have only n symbols to work with. That's because our permutation group is Sn. So in Sn we are dealing with the permutations of what? Of these symbols only. So while you are writing something general like this, if your symbols somehow they cross the threshold of n, then that means there is something wrong. Here however there is no problem. Even when k is n minus 1, the largest possible value, still k plus 1 is n. So it's within the limits. Okay, fine. Now note that this equation helps us reduce things. In what sense? It helps us reduce the sizes of these symbols, if that makes sense. I mean, how the symbols look, they look like numbers. Actually they are not numbers, but they are just some labels, but still we can reduce the labels. Here you have k plus 1. You can subtract 1 from each of these labels and have k minus 1 and k. But then again, with this one also you can do the same thing. and have k minus 2 and k. In another such equation where you will have this 2 cycle on this side and in the middle you will have k minus 2 comma k, and you can continue like this. Ultimately what you will have, you will have 1 comma 2 here. So just to show you what we are talking about here. So you see this equation. Another equation will look like this. Okay. Now if you substitute the expression for this here, what do you get? You will get sigma inverse times this 2 cycle times sigma. That means using these two equations you have this. So if you are subtracting 1 from these things, from the labels here, then you have minus 1 here, and 1 of course it's there, although we are not writing it. Whereas if you subtract 2 from these two things, here you get k minus 2 and here you get k minus 1, then you have minus 2 and 2 here. In general, what do you have to subtract in order to get 1 and 2 here? Naturally, in order to get 1 here, you would have to subtract k minus 1 from k, of course. I mean from these symbols, you have to subtract k minus 1. If you do that, you will get 1 here and 2 here. But correspondingly, what shall you need here then in the exponent? That in the exponent, in that case, you will have to have minus of k minus 1, and here you will have to have k minus 1. So that's the thing we are next going to write. Let me just write it and then you will understand what is it that I was talking about. Hence, this is equal to sigma to the power minus of k minus 1 times 1 comma 2 times sigma to the power k minus 1. Okay, because we keep on reducing and eventually we will get to this. Now this thing in fact is, this of course is our tau. So this thing becomes sigma to the power minus of k minus 1 times tau times sigma to the power k minus 1. But now the curious thing that we notice here is that in this product the elements involved are sigma and tau. And because our subgroup H is being generated by sigma and tau themselves are of course elements in this subgroup. Because you see, by the definition of that type of, subgroup generated by some subset, that subgroup also contains that subset. Okay, among other things, that subgroup also contains all the elements of that subset. So that's why H would naturally contain, it will contain other things also, but among them sigma and tau are also members. So now if sigma and tau belong to H, then this product by closure, existence of inverse, all those things, this also belongs to H. So now see what we have ended up proving. Oh, we need to mention the range for K also. For all K varying from 2 all the way through up to n minus 1. And what does that mean? If we really write the values, let's see what we have here now with us. What do we get when we put K equal to 2? We get 2, 3. We have proved that this belongs to H. Fine. Then you take another value, the next one, you get 3, 4. This 2 cycle also belongs to H. And like that you go, and eventually when you put K equal to n minus 1, the largest possible value, then you get n minus 1 n belonging to H. And along with all these things, already your 1, 2 is there in H because it's your tau. So we have proved that all of these 2 cycles, 1, 2, 2, 3, 3, 4 and so on up to n minus 1, n, they all are elements in H. Next, again we are considering something like that. Next, for all integers K satisfying these inequalities, we have, okay, this time 1, K plus 1. This one turns out to be equal to 1, K times K, K plus 1. Let me continue from here. You understand, it's just product. Again 1, K. Now, unlike this equation, which takes some effort to understand or to see that it's true, here, however, we can readily see that it's actually true. Let's see. Keep in mind, again, I'm saying I will keep repeating this as many times as one needs to repeat, because it's a source of great confusion. In this text in algebra, we are writing the value of the function f at x like this, whereas usually we write that same thing like this. Because our permutation is after all a function, so for us the argument of the function, that is the input, we will put to the left of the function. That means if you are treating this product as a function, which it is, and applying it to some symbol, which of course is coming from our original set having n symbols 1, 2, 3, etc. to n, so that x would appear on this side. And that's why naturally when you start applying this product, you would first of all apply 1, K to that x. Then whatever comes out as an output, on that you are going to next apply this one, and then on that you would apply this one. So that's why when we are calculating the product, our calculation starts from left side and moves rightward. However, for algebra texts where this notation has been adopted, which is more usual, there the input will appear here. So for them, they are actually applying this one first, and then on the output they are applying this one, and then on the output of that they are applying this one. So while calculating this same product, they will start from here and their calculation will move leftward. But for us, it just starts in the natural order in which things are appearing. Okay, so let's see now, what are we really getting this? First of all, this 2 cycles will send 1 to k, and then that k will be sent by this 2 cycle to k plus 1, and that k plus 1 is unchanged by this because it does not change k plus 1. So 1 goes to k plus 1. Fine. What about k? Because k is making an appearance here, we need to see that also. First, k is sent to 1 by this one, and then that 1 is unchanged by this one because 1 is not among the symbols present in this one. And then so that means k is sent to 1, 1 remains unchanged by this one, and then that one is sent back to k. So this entire product sends k to k, that means it does not change k. So k does not appear. Fine. What about k plus 1? K plus 1 is unaffected by the first one. Then the second one sends k plus 1 to k, and then the third one sends that k to 1. So that means k plus 1 is sent to 1. K plus 1 is sent back to 1. So yes, this product is correct. Okay, now you will see a very nice thing. Since tau equal to 1 comma 2 belongs to h, the last equation above implies this belongs to I need these things. Okay, let me just keep it for now. 1 plus k also belongs to h for all k satisfying these inequalities. But how? Let's see. So when we put 2, k equal to 2, we are getting 1 comma 3. So what are we getting from this equation? When k is 2, when k is 2, then we get, let me write it here, 1 comma 3, that is equal to 1 comma 2 times 2 comma 3 times 1 comma 2. Okay. Now 1 comma 2 and 2 comma 3 are both in h. 1 comma 2 is of course our tau that was originally in h, but 2 comma 3 also belongs to h. This we have this result from here. Where is it? Oh, I think I wrapped that up. But anyway, we have the thing written here in details. So 1 comma 2 and 2 comma 3 both belong to h. So 1 comma 3 now also belongs to h. If we put the next value of k, say k equal to 3, then we are going to get a similar equation. 1 comma 4 is equal to 1 comma 3 times 3 comma 4 times 1 comma 3. Now 3 comma 4 is in h, that we already know, but just now we have shown that 1 comma 3 also is in h. So again, using all these facts, this also belongs to h, and if you continue like this, you will end up having this. Okay, so these things, in fact, each one depends on the previous one, but after all of the things which look like this, all the 2 cycles which look like this belong to h for k varying from 2 to n minus 1. So what are the 2 cycles that we are getting this time? 1 comma 3, 1 comma 4, like that, all the way up to 1 comma n, which of course you would get by putting k equal to n minus 1 in this equation. and along with all of them 1 comma 2 of course is also again in H, that we already know. Okay, so now we have known that this kind of 2 cycles also belong to H, where one of the symbols is 1 and the other symbol is something else. And finally let I comma j belonging to Sn be any 2 cycle. Okay, it's necessary to mention that I comma j is in Sn, because otherwise if we are just simply saying the 2 cycle I comma j, then we won't know whether the symbols I and j are from that set of the first n natural numbers or not. If you just simply say a 2 cycle, that may involve any symbols. Okay, if I is equal to 1 or j is equal to 1, then of course I comma j belongs to H. Why? Because that's what we have just now proved, and this part of course is not, this is not a part of the solution. I just kept it for our own understanding. So let me just get rid of this. After this we are continuing like this. Okay, so in that case we are having the fact that I comma j belongs to H. So assume that I and j are both different from 1. Now the 2 cycle I comma j can itself be written as a product of some things. Is it really true? Let's see. 1 goes to I. Note one more thing, but before we see whether this calculation is true or not, let's just see that because I and j are both different from 1, these are actually 2 cycles. Okay, and in fact if I is equal to 1, then this does not make sense, because this has to be a permutation. So it cannot, well, in that case will it be meaningless? No, it won't be actually meaningless, it will just be useless, because if we have 1 comma 1, that just means that the corresponding permutation sends 1 to 1, and also it does not affect the other things. That means it is the identity permutation. Okay, so but anyway we are not considering that case, because I and j are different from 1, so you are looking at 3 2 cycles. Okay, now comes the question of this equation being true or not. 1 is sent to I, then I is unchanged by this, and that I is sent back to 1, that means 1 is unaffected by this entire product. Did you notice one thing? I said 1 is sent to I and then I is unchanged by this. I will actually be unchanged by the middle one if I itself is not here among these symbols. I is of course not 1, but I is also not equal to j. And where is that coming from? That is coming from the fact that we are considering a 2 cycle I comma j. So from the fact that this is a 2 cycle, I and j are distinct, so that's where it's coming from. So that means 1 is unaffected by this entire product, what happens to I? I is first sent to 1 by this one, and then that one is sent to j by this one, and then that j is unaffected by this, so I is sent to j, I to j. What about j? J is unaffected by the first one, j is sent to 1 by the second one, and then that one is sent to I by the third one, so j goes to I. Yes. But now we have all the things we want. Should I also mention here the fact that among these elements, that is the two cycles where one of the symbols is 1, the tau element 1, 2 is also one such. Let me just write one sentence here. So 1, say m belongs to H for all m varying from 2 to n. This time n because we have just m. Here we had n minus 1 because we had k plus 1. Yeah, now from this sentence we know that any 1 something, and where that something is not equal to 1 is in H. So this thing belongs to H. So that means we have proved that any 2 cycle in Sn is in fact in H. And now finally, already we wrote finally, so this is finally. We know the fact that any permutation whatsoever in Sn is actually a product of 2 cycles, some 2 cycles. From that, it now follows that any permutation in Sn is actually in H. In other words, Sn is a subset of H, but H is already a subset of Sn, so they are equal. So that way, H is equal to Sn. And that, what is that result? Apply lemma 2.10.2. So, hence we already have a so here, hence by lemma 2.10.2, not elaborating any further on this, just simply writing like this. This is happening because we have just now proved that any 2 cycle is in H, and by this lemma we know that any element in Sn is a product of 2 cycles. So by closure property, Sn is in H. Combining this with this containment that H is also contained in Sn, we have H equal to Sn, and here the solution ends. Do you see that this, the result in this exercise tells us something else also, namely that if you have a subgroup, not necessarily a subgroup generated by these two things, but any subgroup, say K, of your symmetric group Sn, such that these two things belong to K, then K must also be equal to Sn. Why is that so? That is because this is our tau and this is sigma. If tau and sigma both belong to K, then K is a subgroup of Sn containing the set consisting of tau and sigma, whereas the H that we are looking at here is the smallest subgroup containing this set. So H is by definition contained in K, and K is contained in Sn, but we know that H is equal to Sn, so K is forced to be equal to Sn. So if you come across a subgroup in Sn about which you don't know many things, but the only thing you know is that somehow you either it's given or you end up somehow proving that these two things belong to K, then automatically you know that K is equal to Sn. Okay, let us now see the next one. The next one is the start one. Start means, of course, Herstein somehow thought that these were more challenging than the usual ones, unstart ones. Prove that for in at least 3 the subgroup generated by the 3 cycles in Sn is An. Okay, now what is this is also something similar. So this time we are not just considering 2 cycles, but in fact all 3 cycles, all cycles of length 3, and that is our set now. Our set S now consists of all the 3 cycles in Sn, and we have to prove that the subgroup that S generates is the alternating group of degree in An. Okay, so let's see. So in this one, N is at least 3, of course, okay, because if N is not 3, then we will not get any 3 cycles. If the symbols that are available to us, which we are permuting in fact, if the number of symbols does not reach 3, then these are the only 2 symbols, so there is no question of having 3 cycles. So that's why N is at least 3. And here let me start like this. Let the subgroup of Sn generated by the 3 cycles. The 3 cycles means all the 3 cycles. B H. Like before, let's just call it H. Okay, now we want to look at this. Or should I show the containment that H is contained in AN first, or let me just first say why AN is itself contained in H, since every 3 cycle is AN is contained in H. No, H is contained in AN. Since every 3 cycle is an element of AN, yes. Yeah, even in these things, things can become confusing. Since every 3 cycle is an element of AN, we have this thing. Why? That's because all the 3 cycles are in AN, so AN becomes a subgroup of SN containing the set consisting of all the 3 cycles. So the smallest subgroup H containing all those 3 cycles would naturally be contained in AN. The smallest subgroup is the smallest such subgroup, whereas AN is any such subgroup containing all the 3 cycles. Now, on the other hand, we have this. Any element in AN is a product. If we take just simply any element, then okay, not any element, any non-identity element, let's just take that. Any, because there is no point taking considering the identity element. If the identity element in AN is anywhere, it is also in H. Now any non-identity element in AN is a product of an even number of 2 cycles. Why? That's because they are all even permutations. So from the definition of even permutations itself, each one of them should be a product of an even number of 2 cycles. And I have something else to say, so I am putting semicolon. In any such product, adjacent 2 cycles can thus be paired because there are an even number of 2 cycles, so we can take 2 of them. I mean, first you take one, you consider the first one, and then you consider the next one, you consider them together. That is, you pair up all the things, and they will be paired up like that because the number of them is even. And now each such pair will look like one of these 2 cases. each such pair is of this form A comma B times C comma D, or A comma B times A comma D, where A, B, C, D are distinct symbols. You just think of it, you will realize that these are the only two possibilities. Many questions arise regarding this claim. Why not C comma D times A comma B? That's because disjoint cycles are mutually commuting. So C comma D times A comma B, if they are all distinct symbols, is also equal to A comma B times C comma D. So you don't get anything new by considering that. The only thing new that you can do is having one of the symbols among these four be equal to, having only three symbols here. Why not two symbols? Yeah, that's the question also. Why not just two symbols? One symbol, of course, will not give us anything other than the identity. But what happens if we have only two symbols? A we have, say we have A. What about B and D being equal? So we are going to write that next. We are not considering pairs like A comma B times A comma B since they vanish. Why? That's because we know that a 2 cycle is its own inverse function. So if you have two of them here side by side, then they just cancel each other out and nothing is left, identity. So in the product, if we ever encounter any such thing, it will just simply vanish and the other things will come together and the product will become shorter in terms of the number of cycles. And if you still want something else to also be addressed, A comma B and B comma A in fact are the same thing. Why is that so? This is only true for a cycle of length 2, not for higher length cycles. What is this cycle? This cycle is a function which maps A to B and B to A. But this is also one such function doing precisely the same thing, so they are in fact equal. So that's why these are the only two possibilities. Now, what about the first one? The first one turns out to be equal to this product. This 3 cycle A comma C comma D times this 3 cycle A comma C comma B, and the second type of product is just equal to a single 3 cycle A, B, D, I think. Yeah. Okay, so now what do these things mean? These things mean that, say you take because we are talking about any arbitrary element in an, so that element in an looks like a product like this, where here you have a 2 cycle multiplied by another 2 cycle, here you have 2 more 2 cycles, here you have 2 more 2 cycles, something like that. Or let's not put n here because we already have n. It says ck plus 1. Now we are saying that each of these pairs is either this or this, and accordingly either this or this. So that means each of these pairs is after all a product of 3 cycles. They are already products of 2 cycles, but actually also they are products of 3 cycles. If this one, for example, is of this type, then it's a product of these 2 3 cycles, A, C, D, A, B, D. Whereas any other one, say this one is of this second type, then it's a single 3 cycle. So once you write these 3 cycle representations for each of these pairs, you end up having a product of 3 cycles actually. And a product of 3 cycles is of course in the subgroup generated by the 3 cycles, that is H. So that's why any arbitrary element in an has been proved to be in H also. So that's why an is also a subset of H, or rather I should say a subgroup of H, just like H has been shown to be a subgroup of an in a very easy manner. This proves, we just directly write the conclusion, this proves that an is contained in H. Now combining this with the relation that H is contained in an, we get H equal to A, and here the solution ends. So what this one is saying, let us just again say that you are in the symmetric group Sn. There you consider all the 3 cycles. The subgroup that they generate is in fact nothing but an, the alternating group of degree n. That's the thing. And I am going to end the video here itself because these parts are becoming, you may have noticed, these parts and these exercises solutions are becoming more and more complicated as we go further and further down the lane. So it's better to have these things in easily digestible, palatable chunks than to rush through it, have many things at once and then get overwhelmed by all of them and then just leave the thing entirely. Instead of that, let's just take 1 or 2 things at a time and understand them fully. So I am ending this here itself, but before I do that, actually let me just tell you about the next exercise. In the next exercise, we are given a subgroup of some subgroup K of an itself, the alternating group of degree n, and the hypothesis is that K has at least one 3 cycle. Okay, not all of them, but I mean anything like that, but only at least one 3 cycle. Then K has to be the entire an itself. If I am remembering correctly, that's what this exercise is about, the next one, which we will of course see in the next group theory video on Herstein's algebra. So let me just wrap things up here. If you want to make any If you want to say anything about these things, positive, negative, anything, any thought, you can write in the comment section below, or you can mail me. My address will be there in the description. The link will be given there. And tomorrow, okay, so last Saturday, what did we do? I think we solved Gallian's group theory exercises. So tomorrow let us do Gallian's ring theory exercises. So that's just it. So see you tomorrow, and until then, this is me, Lucifer, from a mathematical room. Have a nice night.